In the field of computational fluid dynamics, or CFD, there is a saying, the upper limit of simulation depends on the algorithm, the lower limit depends on the mesh. Every simulation engineer's growth story is essentially a tale of love and conflict with mesh. Throughout the simulation process, the most exhausting part isn't optimizing the solving algorithm, it's the tedious and repetitive mesh adjustment. To understand why mesh is important, we must first return to the essence of CFD. CFD can be viewed as a virtual laboratory, recreating the real physical world inside a computer. But you know, the physical fields in our real world are continuous. Pressure, temperature, speed, they exist everywhere, but computers can't handle this infinitely continuous information. So what do? We must use the core idea of calculus. Differentiate first, then integrate. For example, you divide a long curve into many segments. As long as you divide them into enough segments, these small curves can be approximately treated as line segments. You calculate the length of the segments, then sum them up, and you'll know the length of the curve. It's like the method of slicing circles we learned in elementary school. Calculating the area of a circle using triangles, isn't that how it's done? Computer simulations follow this same path. First, differentiate to divide the computational area into millions of small units. Each of these tiny units is called a mesh. Within the mesh, we can assume the variation of physical quantities is simple. For instance, if it's linear, then it's easy to calculate. Once everything is calculated, integrate it to understand the entire area. So you can surely think of this. The accuracy of the calculation depends on the fineness of the mesh. If the mesh is too coarse, what's that equivalent to? It's equivalent to using a square to approximate a circle, then the error would be enormous. If the mesh is very fine, your calculations are likely to be more accurate. But the computational load also increases. Do you know the price of memory sticks these days? The money you earn from simulations probably won't be enough to buy memory. Too coarse doesn't work, too fine doesn't work either. So engineers must find a balance between accuracy and speed. Let it be coarse where it should be coarse and fine where it should be fine. What's the principle? Wherever the physical quantity changes most dramatically, the mesh should be densest. For example, near the wall, because of the boundary layer, there's a large velocity gradient. The temperature gradient is also large, so you need to draw a boundary layer mesh that may be so fine that it's beyond comprehension. For areas where shocks and vortices occur, pressure, temperature, and speed change dramatically, so the mesh must be densified. If it's too coarse, you won't see these changes at all. In this whole process, you first need to predict which position might have shock waves or vortices, and then manually mark out a refined area. But you're not a magician. It's hard to get it right in one go. So it's common to first draw a mesh and compute, then see where physical quantities change dramatically, densify that area, and create a second mesh, recalculate, and after obtaining the results, check if key indicators like lift, drag, and temperature have changed compared to before. If the change is significant, it indicates your mesh is still not refined enough. Or maybe you've refined the wrong area, so you have to refine it and recalculate. It requires many rounds of repetition. Finally, you'll find that key physical quantities no longer change due to further mesh densification. That means your calculation result is accurate, no longer affected by mesh-induced errors. If you've done simulations, you know what this step is called. It's called mesh independence verification. Writing reports, papers, or doing projects can't do without this step. Otherwise, your simulation will have bugs. Grid independence verification. This step, it is truly tedious and dull. It lacks technical content, but it's essential. It can take up a lot of your time. When it comes to writing your weekly report on Friday, if you say you spent 3 days this week doing mesh independence verification, you might still feel a bit guilty, clearly exhausted, but it feels like you haven't done any work. Moreover, if you think carefully, theoretically speaking, a set of mesh is only suitable for a specific condition. What does that mean? For example, if you want to calculate the wind resistance of a car at a speed of 60 and a speed of 120, can you use the same mesh? Strictly speaking, no, because with different speeds, the car's wake region is different. Another example, calculating an aircraft's shock wave at Mach 2 and Mach 3. Can you use the same mesh? Actually, no, because different Mach numbers have different Mach angles. The shockwave won't be in the same location. Let's take another example. In liquid cooling calculations, if you change the working fluid, like from water to ethylene glycol, the thickness of the boundary layer would change, wouldn't it? This change means you'd have to perform the grid independence verification all over again. Just thinking about it is discouraging. So you might wonder, is there a way for the algorithm to automatically figure out where to refine the grid? In theory, if I know a physical field, I know the physical gradients. Why not just let the software automatically and repeatedly refine the grid? Great idea. The well-known Chinese domestic industrial software company Qianfu has independently developed the thermal fluid simulation software AI-CFD, which now integrates AI mesh functionality. Once open, you only need to draw a basic coarse grid covering the geometry. Then, as the software runs the calculations, it monitors changes in the physical field, automatically calculates the gradients, and dynamically refines areas with large gradients as it computes. Although grid independence verification still needs to be done, you don't have to do it. It's handed over to the machine. That makes it much easier. This whole process not only saves time, but also enhances the reliability of the simulation. When humans refine grids, there's inevitably subjectivity, and it's easy to overlook small vortices or local hotspots. Overall, a good tool should free people from the inefficient labor of grid independence verification. When engineers are no longer doing these tedious processes, they can slack off better. When you get tired of slacking off, go think about deeper engineering problems, and only then can you come up with better design solutions.